Okay, Calculus 12 students, this is the second video review for the Chapter 5 unit test. Last video I did a bunch of related rate problems, so for this video I will start off by doing a few max-min word problems. Now, max-min word problems, they're different from related rates because you're not taking the derivative with respect to time. Instead, your goal is to find a formula that works within that problem. Make sure you have one variable in that problem and then take its derivative and set it equal to 0 so that you can find a max or minimum point. Okay, so I want to start off this video by going over a question with a cylindrical can. So the question is, what is the radius of a cylindrical soda can which has a volume of 512 cubic inches? And we want to make sure that we can find the radius so that we can minimize the area of the can. Alright, so let's go ahead and collect some information from this problem here. The first thing I'm going to recognize is that I have a volume here of 512 cubic inches, so that's going to be inches cubed. And the good thing about this question is I'm given two formulas. I'm given the volume of a cylindrical can and the area of a I'm giving the area and volume of a cylinder here. So a cylinder looks like this. A circle on the top with the sides there and a circle on the bottom. Okay, so for this kind of a question, I want to minimize the area of this soda can. So this is my soda can. Alright, so I know that my area is going to be 2 pi r squared. So the reason why I have a 2 there is because I have a top here and a bottom, so that's 2 circles, plus the body, I guess, which is going to be the height times the circumference of a circle there, so that's 2 pi r. Okay, so there is my area formula. Obviously I want to minimize this expression here because it says minimize the area. The problem is I do have an h here, okay? So the goal to these max-min problems is that you want to make sure you just have one variable in your equations before you take the derivative. So I have an r and h. The goal is, since I've done this problem a few times, let's go ahead and try to eliminate this h. And how do I eliminate that h? Well, I have to use the volume formula. So the volume of a cylinder is pi r squared times h, and in this problem I know that the volume is going to be 512, and that's going to equal to pi r squared times h. And if I go ahead and isolate for h here, h is going to be equal to 512 divided by pi r squared. Okay, so here's an expression for my variable h. So going back to the original formula here, here's my h here. Let's go ahead and replace that now with let's substitute that with our new h value. So this would be 2 pi r squared plus 512 divided by pi r squared, and then let's times that by 2 pi r. Okay, so notice that now that I made that substitution step there, I only have one variable, which is the variable r, which is good. What that means is I can probably go ahead and take the derivative and set equal to 0. Before I take its derivative, let's go ahead and just simplify this problem just a little bit. Usually when you do simplify, taking the derivative is a little bit easier. So it's 2 pi r squared, and then I notice that this pi here and that pi can cancel off. This r and 1r can cancel off, and then if I take this 512 and times it by 2, I'm going to get plus 1024 divided by r. So there's that lone r right there. And what I'm going to do here is I'm just going to delete this r, and I'm going to put the r on the numerator and put a power to the -1. Okay, so there it is. There is a more simplified version of my area formula. And now I can take its derivative and set it equal to 0 because I'm trying to find the radius that will minimize the total area here. Okay, so the derivative of a is just a prime, and this is going to be 2 pi. This 2 pi right here is that 2 pi right there. That's just a constant, so I'm just going to move it to the front. And now I need to take the derivative of r to the power 2, so that's going to be 2r. it's going to be 2r because I'm just taking the regular derivative. I'm not taking the derivative with respect to time. I'm just taking the derivative. So I don't need to do the dr by dt in this example. And then minus 1024 r to the power of minus 2. Okay, so there's my basic derivative there, and before I take my derivative and set equal to 0, I'm going to go ahead and simplify this a little bit more. This is going to be 4 pi r, and simply just take this 2 and take that 2, multiply those together to get the 4, minus 1024 divided by r to the power of 2. So what I'm going to do here is, since I have r to the power of minus 2, I'm going to just put that on the denominator, because when I'm solving for r, it's much easier to have positive exponents. Okay, so once I've taken my derivative, let's go ahead and set equal to 0. So I'm going to go ahead and delete that and just put a 0 here. All right, so when I take the derivative and set equal to 0, basically what I'm doing is I'm trying to find the critical numbers here. So let's go ahead and do some algebra here. This is going to be 1024 divided by r squared. I'm just taking this term here and bringing that to the other side, and that's going to equal to 4 pi r. And then notice that I have an r squared on the denominator. Let's just do a little bit crisscross there, bring that up top. That's going to be r cubed. And then I'm going to take this 4 pi and I'm going to bring that to the bottom there. So my final expression will be 1024 divided by 4 pi. And if I go ahead and just cube each side, I'll get the cube root of 1024 over 4 pi. Okay, so this is the radius value that will minimize the total area. And one question that I do get from students is that, how do you know whether this radius value is going to be a max or a min? Well, because the problem says we need to minimize, the area, chances are your critical number here, this is indeed a critical number, that will definitely be a minimum. If it's not, then it's very difficult to really finish off the problem. But let me just go ahead and just prove it to you that this value is indeed a minimum. If I just go to my calculator and if I just put this into my calculator, I should get something like 4.36. And if you want to verify that this is indeed a minimum, just draw a number line, set up the first derivative test. This is 4.36. And if you evaluate your area here, which is a prime, that's the same thing as 4 pi r minus 1024 divided by r squared. If you go ahead and find some test values on the left and the right hand side, you'll notice that this side will be positive and this is negative, and you can verify this in your calculator here. Just take some random points like 10 and maybe 1 there, you get positive and negative values. And if you're negative, it's going down, your graph is going like that, and then if it's positive, you're going like that. This right here is a minimum. Okay, so it's kind of going like this. That's a min. All right, so that's how you solve that problem. Let's go ahead and do the next problem. Okay, so question number 6. Find the closest point on the curve y equals x squared to the point 1, 4. Okay, so basically for a problem like this, let's just kind of draw what's going on in this problem here. I mean, this is basically, this right here is a basic parabola. Basic parabola from your pre-calc 11 class. The domain here is all real numbers. And now, where is this point 1, 4? Well, 1, 4 is roughly, here's 1, so maybe this is the point 1, 4. Sorry, that just didn't work out so well. Hold on, this is going to be 1, 4. Okay, so what you want to do is you want to find the shortest distance between this point 1, 4 and the curve y equals to x squared. Now, I didn't really talk too much about this in class, but the shortest distance, or the closest point between 1, 4 and that curve is actually the line that's actually perpendicular to the curve. So this is perpendicular, that's going to be the shortest distance. So this right here, this red point right here, this point x comma y, that's going to be your closest point on the curve to the point 1, 4. So let's go ahead and try to find what these we need to go ahead and find what the x and y values are. Now, in order to do a kind of a problem like this, in my class notes, I believe I used a distance formula in the notes. And let's just go ahead and try to set up the distance formula here. I mean, if you know that the shortest distance is that line that's perpendicular to the curve, you can go ahead and kind of make yourself this triangle right here. Okay, I'm going to go ahead and make that red triangle here. And this vertical distance is going to be 4 minus y, and the horizontal distance is going to be x minus 1. Okay, and if I go ahead and draw this right angle triangle here, this is like the shortest distance. Okay, so if I had to write an expression for this whole this yellow triangle right there, it's going to be d squared equals to x minus 1 squared plus 4 minus y squared. Okay, so do take a little bit of time and just trying to verify for yourself that if you do make this triangle, if this is d squared, this is indeed going to be 4 minus y, because this highest point right here, this point right here is 1 comma 4. So this whole height right here, the whole height is going to be 4, and this point right here is x comma y. So I mean this distance right here is going to be y, and in order to get this expression right here, which is 4 minus y, I mean all you have to do is just take this blue distance and subtract it from this y distance in order to get the yellow distance right there. So hopefully the 4 minus y doesn't really confuse too many students there. Okay, so this expression right here, if I go ahead and square root the d, this is going to be the square root of x minus 1 squared plus bracket 4 minus y squared, and this expression right here looks very similar to the distance formula, which is exactly the same way that we solved this problem in the class notes. Now, if we want to find the shortest distance, we want to minimize this. So in order to minimize something, we need to take its derivative and set equal to 0. The problem is that I have this y variable right here, and I have this y variable right there. So we need to go ahead and replace that. So I do know that y equals to x squared. That's given to me in the original problem. So let's go ahead and delete this guy right here and replace that with x squared. All right. So all I'm doing is I'm just doing a very basic substitution step right there. Now in the notes, the next thing I did was I went ahead and expanded the insides. So this is x minus 1. Let's go ahead and expand the inside here. And yeah, just a heads up, this question does have a fair bit of algebra here. So if I go ahead and simplify everything here, I mean, I'm not going to go through the mathematics behind this, because I do hope everyone can do this by now. This is going to be x to the power of 4 minus 7x squared minus 2x plus 17, and that's going to be my distance is the square root of that. Okay, so now that I have my distance in terms of one variable, we need to go ahead and take its derivative. Alright, so before I start taking the derivative of this expression right here, I'm going to get rid of this square root sign and rewrite that as a power to the 1/2. Alright, now let's go ahead and take its derivative now. This is d prime. And using the power rule, that's going to be 1/2 in the front times 4x cubed minus 14x minus 2. And that's going to be all to the power of... Sorry, I totally botched that. I don't know what happened there. Okay, sorry. That's going to be... Sorry, this part stays the same. I apologize for that. Power rule first. And then I use the chain rule, which is the derivative of the inside there, which is 4x cubed minus 14x minus 2. Right? Okay, and then once I've taken the derivative, I need to take my derivative and set equal to 0. So I'm going to erase that and put a 0 here. And before I can take my derivative and set equal to 0, let's go ahead and simplify this a little bit. This is going to be 4x cubed minus 14x minus 2 all divided by this whole expression right here, because we have the power of the negative 1/2 there. So I need to put this all on the denominator here. So this is a 2, and this 2 right here is that 2 right there, and then I take the square root of all that, which is going to be x to the power of 4 minus 7x squared minus 2x plus 17. Okay. All right, so I have this rational expression, well, I have this weird expression right here. It's not quite a rational expression, but I have a fractional expression right here. And remember, whenever you're taking a fraction and setting the fraction equal to 0, you just need to focus on the numerator. Okay, so you take your numerator and just set that equal to 0, because if your numerator is equal to 0, that means your whole fraction is equal to 0. So basically what you're solving now here is you're taking 4x cubed minus 14x minus 2 and set that equal to 0. Now the reality is solving a polynomial like that is actually quite hard to do by hand, and it will take you a very long time to do it by hand. So I recommend that you go to your graphing calculator, go ahead and graph it. If you graph it, you should get something like this, something like that, and then go ahead and find your zeros. So here's a root or a 0 right there. That's going to be 1.94. This is going to be negative 0.143, and this final point over here is going to be a negative 1.79. Okay, so those are my critical numbers. Okay, so remember, this is actually the derivative. This is like f prime of x. This is not the original function, this is the derivative. So my critical numbers are x1 equals to negative 1.79, x2 equals to negative 0.143, and my third root, or my 0, is going to be 1.94. So these are my critical numbers. All right, these are my critical numbers. Now in this problem, I want to find the closest point, right? So if you're finding the closest point, you want to minimize the distance. So out of all these critical numbers, we have 3 of them. Which one gives you a minimum value? Well, I don't know off the top of my head, so in order to determine whether I have a max or a min, I need to use the first derivative test. So let's go ahead and do the first derivative test, and let's put these values up on a number line here. This is going to be 1.94, this is going to be negative 0.143, and this is going to be a negative 1.79. Now the good news is I already made a little graph right here on this part here in yellow. I have the graph right here, so I already know where my number line is going to be positive and negative. Here it's going to be positive because you're literally above the x-axis right here, and here you're negative, so you're negative there, and over here you're above the x-axis, so that's going to be positive. And this right here to the left hand side, we're going to be negative over here, so this is all going to be negative. Okay, so that's great. So this is going to be f prime of x, right? This is your first derivative test. Alright, so this right here is going to be a minimum because I'm going down and then up. This is going to be a maximum right there, and this is going to be a minimum right here. Okay, so my minimum values are here and here. Okay, now which one of these answers actually makes sense? Well, hopefully you remember from the original diagram that this number will probably make sense, because if you go back to the original diagram here, our goal is we want to find this x value, right? This x value has to be positive, so the value of 1.94, that is indeed an acceptable answer because it's positive and looks roughly right. Okay. Alright, so the goal is I want to find the closest point, right? So I found the x value right there, so how do I find the y value? Well, I know that y equals to x squared, so let's go ahead and plug that value in, 1.94 squared, and that's going to give you a value of, I forget, what does this give you? 3.76. Okay, so the closest point on the graph is going to be 1.94 comma 3.76. So this right here is the closest point on the curve to the point 1 comma 4, which is an outside point. Okay, so I kind of rushed question number 6, but I hope this question is a good review for most of you, because I did do a similar question like this in the class notes. Okay, let's move on to the next max-min problem. Question number 7. Some students have been asking me to do a string question. So I decided to put a string question in the review video here. So once again, this problem is actually quite long and brutal, so be very careful with your algebra. I don't know if I've made a mistake in my in this video yet. I know I made a small mistake in my previous video, so if I do make a mistake, and if you notice it, just please let me know and I'll try to fix it up. Okay, so for this string question, let's see what's happening here. I got a piece of string and it's measuring 20 centimeters and it's cut into two pieces. Great. So one of the pieces is bent into a equilateral triangle and the other is bent into a square. Great. The sum of the areas of the triangle and square is a minimum. Okay, so the sum of the areas of the triangle and square is a minimum. And then the question is asking, what is the length of the piece bent into the equilateral triangle? Okay, so lots of information in this problem. I'm going to start off by drawing a string. And I know that this string is has a length of 20 centimeters. Now this string is going to be cut somewhere. It's not going to be cut in half, but it's going to be cut somewhere. I don't know where, but let's just cut the string right about here. And basically, if I do cut the string, let's go ahead and write a mathematical expression for this. Let's just call this part right here x, that yellow part x. And that means this green part has to be 20 minus x. Okay. Now these two pieces of string, one of them is going to be bent into an equilateral triangle, so that means a triangle with all equal sides. And the other string piece is going to be bent into a square. Great. Now the good thing about a square is that all sides are equal. And the good thing about an equilateral triangle is that all lengths are equal. Okay. Alright, so let's go ahead and write some expressions for the equilateral triangle and the square. Now, for this equilateral triangle right here, if I know that the perimeter is going to be x, that means each length has to be x, which is the perimeter, divided by 3. Okay? And hopefully that's okay. And if I focus my attention now to this square here, if I know that my perimeter is 20 minus x, and if I have 4 equal sides, then each side is going to be 20 minus x divided by 4, and that's going to equal to the length of one side. Okay, so that's step number 1. Write a mathematical expression for the length for the equilateral triangle and the sides for the square. Okay, now we need to go ahead and write some area expressions, because basically the question, if you have some time to kind of read the problem here, it does say the sum of the areas has to be a minimum, right? So we need to write an expression for the areas now. Now the area for an equilateral triangle is going to be root 3 over 4 times L squared. That's the formula for the area of an equilateral triangle. And the area for a square is going to be just s squared. Okay, and don't worry, this formula right here, the equilateral triangle, that will be given to you, so don't worry about memorizing it or deriving it. I will give it to you. Alright, so if I add up all the areas, this is going to be root 3 over 4 times L squared plus s squared, right? That is the sum of the areas. And if I go ahead and do a substitution step here, what is L equal to? Well, L is equal to this guy right here. So let's go ahead and substitute that in. So area is equal to root 3 over 4 times bracket x over 3 squared plus, and then ask yourself, what does s equal to? Well, s equals to this expression right here. So that's going to be 20 minus x divided by 4, bracket, bracket, all squared. Okay, so great. The good news is eventually I need to take the derivative of a, because this is a max-min problem. And the good news is that I have one variable, right? I just see one letter x, so that's great. Now, before you take the derivative, I recommend students to go ahead and simplify this problem as much as you can. So this is going to be root 3 over 4 times x squared divided by 9 plus, put this in brackets, 20 minus x close bracket squared divided by 16. Okay, and then we can take the 4 and the 9, I can multiply those together, so that's going to be root 3 times x squared all over 36 plus 20 minus x squared divided by 16. Okay, so great. I've simplified the problem as much as possible. Let's go ahead and take the derivative of this expression now. So I want to go ahead and take the derivative, which is a prime. Now, one thing that you should recognize right away is I have a root 3 and 36 there. That's a constant. So let's just take the constants and move them to the front. And then ask yourself, what's the derivative of x to the power 2? Well, that's going to be 2x plus, once again, I have a 16 on the denominator, right? That's a constant, right? So let's just move the constants out to the front. And then let's go ahead and take the derivative of this expression right here. That's just the power rule. So that's going to be 2 onto 20 minus x. And then you need to apply the chain rule here. What's the derivative of negative x? Well, that's going to be negative 1. Great, so there's a lot of algebra here. So let's go ahead and continue to simplify this. This is a prime. Sorry, I'll use the black color here. This is a prime. Okay, so one thing that I see right away is this 2 right here and this 36. I can simplify that. So that's going to be root 3 times x all over 18. Over here I have a minus sign over here and a plus sign, so that's going to be a minus there. And then I have a 2 and a 16, so that's going to be an 8 on the denominator, so this is going to be 20 minus x all over 8. Okay, so there it is. There's my derivative. I've simplified this as much as possible. Now the next thing that I need to do is I need to take this derivative and set it equal to 0. So let's go ahead and remove that a prime, put a 0 here. And now that I have two fractions and I'm taking the difference of two fractions, going back to math classes from a long time ago, if I look at my 18 and my 8 here, let's try to get a common denominator here. And what happens is that if I times this side by 4 and times that by 4, and if I times this by 9 and if I times that by 9, I will get a common denominator of 72. So 18 times 4 is going to be 72, and then I can put the 4 over here. So this is going to be 4 times root 3 times x, and 8 times 9 is going to be 72 as well. And then I'm going to put the 9 out in front here and then just delete this 9 there. Okay, so now I have a common denominator, and let's go ahead and just put this all together now. Now if I erase all this, I have a common denominator now of 72, and my numerator was 4 root 3x minus 9 times 20 minus x. Okay, so I'm just putting everything under one common denominator now. And then what we can do next is we can go ahead and just distribute this negative 9 onwards. So if I continue on with this, this is going to be a lot of algebra here. But that's what calculus is. It's a bunch of algebra here. This is going to be 180 plus 9x divided by 72. Okay. And then what I can do next is that I have an x here and an x there. Let's go ahead and factor those x's out. Let's say 4 root 3 plus 9 minus 180 divided by 72. Okay, so I did all that, and I simplified all that, and once I've simplified that, I need to set my derivative equal to 0, so I'm just going to erase all this over here and put a 0 here. If I take this 72 here and if I move that to the top here, that's just going to cancel out. So remember, whenever you have a fraction and if you're trying to set this equal to 0, you just take your numerator and set that equal to 0. So I can just go ahead and delete all this. and that's my expression right here, my numerator equal to 0. Now how do I solve for this? Well, I just bring my negative 180 to the other side, so this is going to be 180 equals to x onto 4 root 3 plus 9, and then I need to solve for this x value here. So if I solve for x, x is going to be x is equal to 180 divided by 4 root 3 plus 9. And there it is. There is my value of x that I can use to finish this problem here. And if I go to my calculator here, this is going to be 11.301. Okay, so after all that work, and I guarantee you this is going to be a minimum. I don't want to do the first derivative test right now because I know it's going to work. Just take my word for it. So I know that x is going to equal to 11.301. So that is the value of x that's going to be used for the equilateral triangle. And if you want to find the value of the length for the square, you just do 20 minus 11.301. Put that into your calculator. I don't know what that is, so I'm just do that right now. 11.301. I get 8.699. You know, I mean, the problem wasn't asking for this, but this is what you would do to go ahead and find out the lengths for both the triangle and the square. Okay, so hopefully that's enough to kind of help people prepare for the string question on the exam. That's it for the max min problems. The final thing that I want to do for this video is I want to go over a few of these graphing questions here. I always find that students are always asking me how do we do these graphing questions, and now on your test you will be given a few of these word problems, max min problems, as well as related rates. But you are also responsible for analyzing first derivative graphs, second derivative graphs, and finding out what's happening to the original graph. Okay. Now, what I recommend for students to do is that there was an in-class assignment in this chapter, and the very first page, you know, these three graphs were given to you. Okay. So basically what's happening with these three graphs is that the first graph is the original function, the second graph is the derivative, and the last graph at the bottom is the second derivative. Now, if you're really struggling with these questions where I give you the first derivative and I ask you what's going on with the second derivative or the original function, then I really recommend that maybe take a few minutes to just memorize this diagram right here. If you have these visual diagrams kind of memorized, then you can always kind of figure out what's going on in the problems just by looking at these diagrams. So I'm just going to go ahead and work through several of these problems using the diagram, and hopefully you'll be in good shape for the test. Okay, so here's a kind of a question that you will see. The graph of f prime of x is shown below. So this is the first derivative. So this whole thing in yellow right here, this is the first derivative, okay? Now, if I give you the first derivative, that's kind of like this middle graph right here. I'm giving you the first derivative. And then the question is saying, find all intervals on which the graph of f is increasing. Justify your answer. Okay, so you're given some information about the graph of the first derivative, and you need to go back to the original graph and find out where it's increasing. Okay, now the very first thing I want to note is that increasing means that f of x has a positive slope. That's what increasing means. Okay, so let's go back to my diagram right here. I'm going to erase this. Now, if I go back and look at my original graph, where do I have a positive slope on my original graph? Well, I have a positive slope from here to here, and I have a positive slope from there to there. Now, how does that relate to my derivative? Well, if I go straight down, I have an x-intercept. So this part seems to match up with that part right there. And this part right here seems to match up with that intercept. So it seems to me, if I look at my original graph right here, it seems to me that if I have a positive slope, which means I'm increasing, that shows that on my derivative, my graph on my derivative represents the values where I'm above the x-axis. Okay. Okay, so let's kind of summarize that right here. So, sorry. If f is increasing, then f prime of x must be above the x-axis. All right. Or another way of saying that is f prime of x has to be greater than 0. Okay, so let's go back to my graph here, my original question now. If I focus on this graph right here, where am I above the x-axis? Well, I'm above the x-axis from here to here, and I'm also above the axis from here to here. Okay, so go ahead and just write an interval. This is going to be between 2 less than x between 4, and this is going to be x is greater than 6, but it has to be less than 9, I guess. All right, so those are your intervals right there. Okay. All right, let's move on to the next problem here. Hopefully that makes sense. All right, so same kind of graph. My derivative is given to me, and now I'm asking find all intervals on which the graph of f is concave down. Justify your answer. Okay, so going back to my 3 graphs here, this is going to be f of x, and this is f prime of x. For this question, I don't care about the second derivative, so I can just kind of eliminate that. So where is f prime of x? Where is this part concave down? Okay, well, I'm concave down from about here to about there. Okay, so if I line this up correctly, there's a minimum point right there. So if I'm concave down, it looks like my derivative has a negative slope. Okay, so basically I'm looking for the intervals where my derivative has a negative slope. If my derivative has a negative slope, that means my original graph is concave down, according to the diagrams from the in-class assignment. Okay, so going back to the original problem now, where do I have a negative slope? Well, right here, this is a negative slope right here from there to there, negative slope, and then I have a negative slope from here to there, and then I have a negative slope from here to here. Okay, so all you have to do now is write an interval representing those blue lines, and then you're good. Some acceptable answers that I like are between 0 and 1. So between 0 and 1, that's one interval, and then between 3 and 5. Between 3 and 5, and then finally you also have a negative slope from 7 to 8. Okay, so those are all acceptable answers where you have a negative slope. Let's move on. Question number C. Okay, so same kind of graph. I'm given the derivative, so this whole thing is the derivative. So I should be focusing on that part right there. Okay, so let me just delete all this. Delete that, delete that. Okay, so the question is, the question is, find all values of x at which the graph of f has a relative minimum maximum explained. Okay, so let's go look at our original function f. Okay, so here is my original function f of x. Notice that I have a max here and I have a min there. Okay, so if I have a max or a min on my original graph, what's happening with my derivative? Okay, so if I draw a line straight down, it looks like I have an intercept right there. And if I draw a line straight down, it looks like I have an intercept over there. So basically, if you want to have a max or a min, your derivative must have an x-intercept. Okay, so x-intercepts are key. So here's an x-intercept, there's an x-intercept, and there's an x-intercept. Okay, now if you want to have a max, it looks like your derivative has to be above the x-axis, and then it has to be below the x-axis. Okay, so if I match that up, then this point right here should be a max. All right, because this part is above the x-axis, and then this part is below the x-axis. Now, if I want to have a minimum, then I have to be below. So on the x-intercept on the left-hand side, I need to be below the x-axis, and then to the right-hand side of the x-intercept, I need to be above the x-axis. So this right here is going to be a minimum, and this right here is also going to be a minimum. Okay, so you have a minimum at 2 and a minimum at 6, and you also have a maximum at x equals to 4, and you would just justify that. In order to explain this, you would just say that the derivative has to equal to, your derivative must equal to 0, and then for a max you must be above the x-axis on the left-hand side and below the x-axis on the right-hand side, and you would say this a very similar argument for the minimum point, and that's it. Okay, let's move on to question number D here. I'm trying to do this as quickly as I can. Find all values of x at which the graph of f. So find all values of x at which the graph of f has a point of inflection. Explain. Okay, so here's my original graph. Here's f of x. Where's my point of inflection? It's about right here, I guess. So if I go straight down here on my derivative, it looks like I have a minimum point, right? So it has to be a minimum. And it looks like if you have an inflection point, yeah, I guess it's, I mean, one thing that you have to recognize here is that if you have a minimum, it just means that you have a slope of 0, right? So you want to find all values on your derivative where you have a slope of 0. So those are your max and your min points. So if you want to find the values of x at which the original function has a point of inflection, on your derivative, you need to find the max and min point. So here's a minimum point right here, maximum point there, a minimum point, maximum, and a minimum point. So all these points have a slope equal to 0. So here, 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 and there. So if you want to have an inflection point, once again, if you have an inflection point on your original graph, that means that your derivative must have a slope of equal to 0, or a max or a min point. Okay, so the answers here are x equals to 1, 3, 5, 7, and 8, and that's it. Great. Let's move on to question number, the last question here of the first derivative here. Let me just see what's going on here. Same kind of graph. The derivative is given to me. And this question is asking find all intervals in which the derivative is increasing. Okay, so this kind of question I don't need to have, I don't need to resort to the 3 graphs. It's because I'm just asking you directly on the graph where are you increasing. So increasing means when do you have a positive slope. And when do you have a positive slope? Well, between 1 and 3, between 5 and 7, and from 8 to 9. Okay, so write an interval representing that. And then let me just kind of erase this in order to do the last question here. The last question is find all intervals on which the graph of f prime is concave up. Okay, so concave up means you look like this, concave up. Okay, so I'm concave up here from 0 to 2. I'm concave up from 4 to 6, and I'm concave up between 7.5 to about 9. Okay, so that's where I'm concave up, so just write your intervals for that. Great. Now before I'm now done with this first derivative, I also want to do another question where, you know, if I'm given the graph of f prime of x, this is f prime of x, how can you graph a possible f of x? So I did this kind of question a few times in class, but I know there's a few students that are probably not paying attention. So here's the 3-step situation on how you graph the derivative of f of x. Now keep in mind, there's more than one answer when you're doing a question like this. And the reasoning is because if my original function is x squared, then my derivative has to be 2x. Now, if my original function is going to be x squared plus 9, if you take its derivative, you actually get the same answer. So you can actually come up with so many different f of x functions, and your derivative will always be the same, 2x. So because of this reasoning, I was telling students that it's kind of like this. If you're a dog, then you have to be an animal. Alright, so for this kind of question, like I said, if you are a dog, then you must be an animal. But if you're an animal, it doesn't necessarily mean that you're a dog, right? You can be a cat or a fish or whatever. So for a question like this, just be prepared that there's more than one possible answer when you're trying to graph the original function. Okay, so what I recommend students to do is I would find the x-intercepts. Okay, so my x-intercepts, here's an x-intercept, there's an x-intercept, and there's an x-intercept. Step number 2 is draw a vertical line, so VL, vertical line at, sorry, I'm getting super tired here, so draw a vertical line at the x-intercepts. Okay, so I'm going to draw a vertical line straight down here, straight down there, and straight down there. Alright, step number 3, determine whether you are above or below the x-axis. Okay, so over here on this yellow part that I'm highlighting, that is definitely below the x-axis, so I'll put a negative sign there. This part in green right there, that's definitely above the x-axis. This is below the x-axis, and this is above the x-axis. Okay, so let me just delete that. Alright, so what you have to do now is, you know, this is pretty much like the first derivative test. If you're going from below to above the x-axis, this means that you have a minimum point somewhere along that vertical line. And if you're going from positive to a negative here, that means you must have a max here and a minimum here. Okay. Now, the reason why you can have so many different answers is that you can put your minimum maximum points anywhere along those vertical lines. So for this very first minimum that I'm highlighting in blue, I'm just going to go ahead and put it just below at the very bottom, just because I want to. And then I have to look at my purple max, and maybe I'll put my maximum somewhere above here. And then I'll look at my blue minimum point, and maybe I'll put my minimum point down here, for example. Okay. All right, now that I've drawn my max and minimum points there, let's go ahead and now sketch the graph here. Going back to the very first region here, I need to have a negative slope here, right? So a negative slope, I'll put this on green here, so maybe this is a negative slope, negative slope, negative slope, negative slope, then it connects to my minimum point. And then I need to have a positive slope, and then so if I have a positive slope, I need to go back up, 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 and then I reach my maximum. And then you have a negative slope, so I'll do a negative slope, down, 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 and then it reaches that minimum point. And then I need to have a positive slope. Even though you have all this weird stuff going on right there, I just need to have a positive slope, so you can feel free to kind of change this up a bit to slower and then increasing maybe, I don't know. As long as you have a positive slope there, that's all I care about. And if you go ahead and just delete everything now, and if I put this here in purple here, this right here in purple is a possible sketch of my original function there. Okay. Alright, so there's a possible graph for f of x. Okay, let's move on. We still have a few more questions that we need to go over. I do want to go over a few more problems where I give you f double prime of x. So this is f double prime of x. It's very similar to the graph of f prime of x. Now, if I give you f double prime of x, what you need to do is you need to be able to go back to the original graph and find a few things. Okay, so for this question, I'm asking find all intervals on the graph of f where I have a point of inflection, and I need to justify my answer. Okay, so I did this question a few times in class here, but I know some students weren't paying attention. So if this is my original graph, f of x, this right here is an inflection point. Alright, it's an inflection point because I'm going from concave down there, and then I'm going to concave up. Okay, so how does this relate to my second derivative? Well, if I draw this line straight down, notice that my second derivative right here, I have an x-intercept. Okay, and basically, if you want to have an inflection point, your second derivative needs to have an x-intercept, but it also has to go from like a negative to a positive, okay, or from a positive to a negative. It has to change signs. All right, so if this is my second derivative, if this is f prime of x, double prime of x, what I need to do right now is I need to locate all the x-intercepts. So here's one, and here's another one. Notice that I do change from below the x-axis to above the x-axis. That's great. That means I have an inflection point. And over here I go from above the x-axis to below the x-axis, so that means I have an inflection point. And here I'm below, and then I go back above, so these are all inflection points. So that's an inflection point, inflection point, inflection point. Okay, so basically for your reasoning, you would just say that in order to have an inflection point, your second derivative must have an x-intercept, and at that x-intercept, it must change signs from positive to negative or negative to positive. And that's it. All right, let's move on to question number B. All right, so same style of question. I'm giving you the second derivative this time. So this is f double prime of x. And if I give you f double prime of x, we need to go back to the original function and see if we can find some characteristics for the original function. So for part B, I want to find all intervals on which f is concave down. Okay, concave down. All right, so if I go back to my original function, this is f of x. This is my original function right here. Where am I concave down? Well, I'm concave down from here to about there, roughly. Now, once again, this is the inflection point. So if I go all the way down to my second derivative, which is f double prime of x, what's happening to the second derivative? Well, the second derivative is below the x-axis. So if the second derivative is below the x-axis, that means the original graph is concave down. So if f double prime of x is less than 0, then f is concave down. Okay, so once again, just find the regions where you're below the x-axis. So in this original graph here, you're below the x-axis, and over here you're below the x-axis. So in those green regions, you would be concave down. And once again, you would just write this as 0 less than x less than 2. This would be 4 less than x less than 6. All right, so those are the intervals where you're concave down. Okay. All right, let's move on here. All right, so once again, I'm giving you the second derivative. So this is f double prime of x. And this time I want to find all values of x at which the first derivative is increasing. Okay, so I'm looking at the first derivative. So here's the sample first derivative, and here is the second derivative. Okay, so where is f prime of x increasing? So that's the same thing as where does f prime of x have a positive slope? Increasing means positive slope. Okay, so I have a positive slope right here from here to here. Okay, so how do I relate this back to the second derivative here? Well, here's an x-intercept, so I need to find x-intercept, and I need to be, the second derivative must be above the x-axis. Okay, so what that means is if f double prime of x, if this is above the x-axis, then f prime of x is increasing. Okay, so on your original graph, just find intervals where you are above the x-axis. So I'm above the x-axis from here to here and from there to there. Okay, so if you want to write your intervals here, this would be between 2 and 4. Sorry, so between 2 less than x, between 4, and this is x is greater than 6, but then x has to be also less than 9. Okay, so those are intervals where f prime of x is increasing. All right, so we're almost done here, I hope, because I'm dying right now. All right, so once again, I have the second derivative here, f double prime of x. I want to find all x values such that the derivative has a relative minimum. Okay, so here is my derivative, f prime of x, and here is my second derivative. Now, it looks to me that I have a minimum. This whole thing is a minimum, right? Okay, so if you have a minimum there, what's going on with my second derivative? Okay, so sorry, a relative minimum. I'm rethinking this. Here's my minimum right here. Sorry, this point right here is my minimum. And if I go right to my second derivative, that means I must have an x-intercept. and then I must be below the x-axis on the left-hand side, and then I also must be above the x-axis on the right-hand side. So I need to look for that kind of behavior on my second derivative. So if I look at my second derivative now, here's an x-intercept, and over here I'm below, and then over here I'm above. So this must be a minimum, right? And over here I also have an x-intercept, and I am below, and then I'm also above on the right hand side, so this must also be a minimum point. Okay, so x equals to 2 and x equals to 6. Those are my minimum points. Alright, so basically for your reasoning, I mean, just say that, you know, f double prime of x has to be equal to 0, and then f double prime has to change from negative to positive. Alright, so this is negative right here, and this is positive right there. Okay, and that's it. And finally, the last question, because I am dying. Great, another f double prime of x. So f double prime of x graph question, and final intervals on which the derivative is concave down. Concave down. Okay, so the problem is with my diagrams I have here on the right hand side. The problem is that this situation right here is actually concave up. Alright, it's concave up. And basically if you're concave up, that means your second derivative must have a positive slope. So if I want to have concave down, this means that my second derivative must have a negative slope. Alright, so find all regions on your graph where you have a negative slope. And basically a negative slope is from here to here, from there to there, there to there, 0 to 1, 3 to 5, and from 7 to 8. Okay, so that's where you'd be concave down. Alright, so I apologize. The last few graphing questions, I didn't give you the greatest solutions in terms of writing your answers down, but if you kind of rewind the YouTube video and hear what I'm saying, I'm pretty sure you guys can put up your own, make up your own sentences to explain why the original graph or the first derivative is the way it is. That's all that I'm going to do for video reviews, so hopefully this will help some of you, and I'll see you guys back in class. Alright, see ya.